Okay, so as in the last video, we started discussing about our first example of simple harmonic motion, and that first example was all about motion of projection of a particle along a circular path. See, here we'll not talk about the motion of the particle, since motion of the particle will be following the uniform circular motion, right? Here you can see, here we have particle, and this particle will gonna follow the uniform circular motion, but we're gonna talk here about the motion of the projection. This is the projection we have, right? We're gonna talk about the motion of the projection, since this projection of the particle or this shadow of the particle will gonna follow the simple harmonic motion, to fro, to fro, right? So this will gonna follow the simple harmonic motion, not the particle will be following the simple harmonic motion. It will be of course following uniform circular motion, but the projection of the particle or shadow of the particle will gonna follow simple harmonic motion along a circular path, right? So now we were writing here the definition of this, the definition of the motion of projection of a particle along a circular path. Let's continue with it. Particle P is moving along a circular path, is moving along a circular path. Is moving along a circular path of radius r, while its shadow, or you can say projection, q. See, we have named the shadow, we have named the projection of a particle as q, and we have named the particle as p, right? So here q means shadow of the particle is executing simple harmonic motion, right? Now let me explain you this example. Simple harmonic motion. Now let's read this definition again so that it must be more clear to us. Particle P is moving along a circular path. See, this is particle P, this is particle which we have termed as P. This is moving along a circular path. See the direction of it. This is moving along a circular path, right? So particle P is moving along a circular path of radius r, ठीक है, while its shadow Q is executing simple harmonic motion. While its shadow Q is executing simple harmonic motion. See, particle P is moving along the circular path, but while its shadow with it, with the action of moving in a circular path, the particle P is producing a shadow, and that shadow we have named as Q, and that Q is executing simple harmonic motion, right? So this I have explained you in very simple words, this definition. What this definition says, particle P is moving along a circular path, which means there is a particle, we have named that particle as P, that is executing uniform circular motion, while with the action of the uniform circular motion it is producing a shadow, it is producing a projection, and that projection, that shadow is executing simple harmonic motion, and that shadow or that projection executes simple harmonic motion, right? Now the definition of the simple harmonic motion and the connection between simple harmonic motion, or you can say circular motion, is clear, right? Or you can say this is motion of a projection of a particle along a circular path, or the second name of it is the connection between uniform circular motion and simple harmonic motion. Now see, we have discussed a definition of it in very detail, right? Now it must be clear to us that why the projection of a particle follows simple harmonic motion, why does not particle follow simple harmonic motion, why does the particle follow uniform circular motion. Now this connection must be clear to us. Now we will gonna drive three formulas for the, you know what, uniform circular motion. What those three formulas would be? Those three formulas would be all about displacement, velocity, and acceleration. Displacement, right? Velocity. These are very, very, very important formulas. We're gonna drive in every video or every example. Velocity, acceleration. In some examples, we're gonna drive the formula for the, you know what, time period, frequency. We're gonna drive the total energy formula for the simple pendulum as well. But here in the uniform circular motion and simple harmonic motion, we're gonna drive three formulas, right? The displacement, the velocity, last but not the least, the acceleration. Now see, we'll start with displacement. Let's make here the diagram, or initially let me mention here the derivation for the displacement. Derivation for the displacement, right? For derivation of the displacement, we must make a diagram, right? Then it must be more clear to us. So this is a circle, and here as you can see, it will make its shadow from here to here, right? It will make its shadow from here to here, and this limit applies that this is the radius of the circle, right? Radius, this is its limit, its large limit, right? So I can easily do not make here the surface, however I must make here the radius, right? And I must say that my projection is now moving along the radius, not on the surface. Now I'm making it move along this you know what, radius, right? So we must think now our shadow of the particle would be here on the radius. Now see, where is our particle? Our particle is here somewhere, which is moving, right? Which is moving, and this is our center point. This is center. Now see, here we have R, right? Here we have R. Now see, where would be the projection of this particle? This projection of the particle would be very straight to the surface, right? Which means if I would have made here the surface, its projection must be here. But now as I'm not making surface here, now I have considered my surface as the radius, right? So now my projection would not be on the radius. Wait for it. Now my projection would be on the radius, right? Now my projection would be on the radius, which means my projection would be here. This is Q point. Since this is projection, this is my projection, and this is P point, since this is particle, and this is of course R, since it is R, radius, right? Now see, we have already talked about displacement would always be away from the mean position. This point is must be noted, that it is always away from the mean position, always away from mean position. Always away from the mean position, which means here would be our displacement, and this I am terming as x, right? Now as you can see this shape, and here of course we're gonna have some angle, here we've some angle, right? Now you can see, we can see a figure in it, right? And what this figure is called, this figure is known as right angle triangle, right triangle, right? This is right triangle. Now see, we are driving the formula for the displacement, right? Which means we must have a function, since we have theta here as well. We have theta here as well. Now we must have a function here which takes base 2 and hypotenuse 2. If I talk about the functions, we have sine. Some people have sine is equal to perpendicular upon hypotenuse, which means perpendicular is also included there in the sine function, and hypotenuse is included, which means we cannot use that. We cannot use the sine function since perpendicular is included in it. Okay, so in sine function the perpendicular is included in it, so we cannot actually use the sine function. But if I to talk about cos function here, what do we have in cos? Cos is equal to base upon hypotenuse, right? So base, which means r, this x would be included, and hypotenuse, which means r would be included, which means yes, we must use cos function. We must use cos function, and cos theta is equal to base upon hypotenuse. Base upon hypotenuse. Base upon hypotenuse, right? Now see, what do we have base here? We have base here x, right? So I can write here cos theta is equal to base, we have x, and what do we have? Hypotenuse here. Hypotenuse is r, so we have written r here, right? Now what will we do here? Now see, we need to find x, since x represents the displacement. X represents the displacement, right? So r is dividing with x here. Whenever we go there, it will be multiplied. So x is equal to r cos theta. R cos theta. This is the formula for finding the displacement. This is the formula for finding the displacement. X is equal to r cos theta. We can generate more formula from it for the for finding the displacement, because we know that the angular velocity, this is angular velocity, and this is equal to angular displacement upon time. This is angular displacement, and this is angular velocity, right? Now see, you need to find theta, since we have theta here, so t is dividing with here, it will be multiplied, so theta is equal to omega t. Theta is equal to omega t. Now let's put this in this formula. So x is equal to r cos omega t. R cos omega t, right? So this is the second formula for it, right? So either you can use x is equal to r cos theta, or you can use x is equal to r cos omega t. So here we have derived the formula for finding the displacement of the projection of a particle moving along a circular path. In the next video, we're going to talk about the maximum displacement and the minimum displacement, where we're going to have maximum displacement, where we're going to have minimum displacement, right? So stay tuned for the next video.